see if we can make some observations that I think you probably already know. Zoom 6, let's get that screen nice and square, or nice and normal. So we're going to zoom 6. And then I just want you to type in this equation, and type it in with the parentheses, okay? Don't multiply it out, just type it in just like this. Just type that in. And take a look at the shape of it. So let's make an observation about it. First of all, how many times does it cross the x-axis? 3. Where do you think it crosses the x-axis? Can you tell? At -2, +1, and 2, right? So 3 unique factors, 3 what we call zeros of the polynomial. Perfect. Okay, now we're going to sketch this one. Now, first of all, does it have basically the same shape? Just in general, like if you were going to air draw it, isn't it basically the same shape?
Yeah.
That's a cubic shape, very typical. What's different about this one though?
Bounces off too.
It bounces off too. I love the word, perfect word. When you have an even powered 0, this is called the multiplicity. This root happens twice. And when that happens, your curve bounces off the x-axis. It does not go through, it bounces. What did it do at -2? At -2, it went through, right? Because that has a multiplicity of 1. Got it? All right, one more. Now, it's hard to tell, but it definitely crosses at 2, right? Which is totally what we would expect. But it doesn't behave the same way it did up here. Up here at 2, I can't remember which way it was going, but I think it went just through like that. Just like zoom right through. Then we do this one. Here, it goes through 2, but it squiggles its way through 2. That is kind of like a point of inflection right there. An odd degree factor. So if the multiplicity is odd, the curve's going to go through the axis, but it's not going to go straight through, it's going to squiggle through. Okay? All right, so let's look at these notes real quick and fill in some blanks, but that is the basics of it. Linear factors, that is factors that happen only once, the curve just slides right through. If you have an even multiplicity, an even power here, it's going to bounce off. And if it's an odd multiplicity, an odd power here, it's going to squiggle its way through. So here we go. Where are some blanks that need filled in? Typically, we know that the graph of a polynomial passes through the zeros on the graph. Normally, it just passes right through. However, when a 0 has multiplicity greater than 1, the graph will behave differently. So, he's drawn one for you here, this function. He graphed it on his calculator. The multiplicity of a 0 is the power of its factor. So for his particular problem, the multiplicity of I'm not sure, something here is not right. Something isn't right for the function he wrote. So let me rewrite this function. 0.01 x plus 4, x plus 1 cubed, and x minus 3 squared. Okay, so what are our roots? What are our zeros of the polynomial? We have 1 at negative 4, we have 1 at negative 1, and we have 1 at 3. The multiplicity of this is 1, which means the curve is just going to go through that point. Here, the multiplicity is 3, which means we're going to squiggle through. And here, the multiplicity is 2. So look at the picture. Does that jive with what happened in the picture? Did we pass through at negative 4, just like we thought? Did we squiggle through at negative 1, and then we bounced off at 3? Perfect. Okay. Some polynomials have roots that contain an imaginary number. This means that you will not see them on the graph, because if they're imaginary, you're not going to see them. These are real zeros. Across, you're not going to see the imaginary ones. So he drew one there for you. Perfect. All right, let's do some problems on the back side. Oh no, I have burning from, but there's more notes. All imaginary roots. So eventually, guys, you're going to be graphing these on your own without the calculator. All imaginary roots come in pairs. I think you already knew that. If a plus bi is a root, then so is a minus bi. So imaginary roots always come together with their conjugate. So if you know 2 plus 3i is a root, then you're automatically going to know 2 minus 3i is a root. So what would be the conjugate of 4i? So if 4i was one of your roots, what's the conjugate? Negative 4i. How about negative I? I. How about 2 minus 3i? 2 plus 3i. How about negative 4 plus 2i? Negative 4 minus 2i. Remember, with the conjugate, it's only the middle sign that changes. The I sign, the one on the I part changes. A polynomial of degree n has exactly n complex zeros when counting multiplicities. Okay, that's a big idea. What it means is, if the degree of your polynomial is 5, there are going to be 5 zeros. Now, some of them might be imaginary, and some of them might be duplicates, but there will be 5 of them. Look at the one he sketched. What is the degree of this polynomial? No, the whole polynomial. What is the degree of this? 6. That means there should be 6 answers. Well, here's 1, here's 3, and here's 2. 6 answers. In this case, they're all real. They can be imaginary. We'll have to learn to deal with that. But whatever your degree is, that's how many zeros you're going to have. All right, so let's look at this next part. Polynomial inequalities. Now we're going to look at do the same basic idea with inequalities. When we write f of x, we are referring to the y value, right? So if f of x is greater than 0, what does that tell you about the graph? That means the graph of f of x is what? Okay, above the x-axis. So if y is positive, that means you are looking at whatever part of your curve that is above the x-axis. And if it's negative, obviously you're looking at the part that is below. So, look at the very bottom of this page. Where does f of, look at the picture, where does f of x equal 0? Where does it equal 0? At negative 3, negative 1, and 3. That's where it equals. Where is it positive? Okay, now this is going to be an interval. Where is it positive? Between negative 3 and negative 1. And where else? From 3 to infinity. Very, very good. Those are the positive parts of the graph. Okay, now where is it less than or equal to 0? Negative infinity to negative 3, and we'll bracket that, right? Since it's or equal to. Where else is it less than 0? Negative 1 to 3. Perfect, perfect, perfect. All right, so now we're going to actually solve some of these without our graphing calculator. Now, if you have a graphing calculator, you can use a picture just like the one we just did to answer. If we don't have a calculator, then here is how we're going to handle it. Your job is to figure out where what x's create a greater than 0 result. Okay, so let's draw a number line, just like we did before. Where should the dots on the number line go? 3, negative 1, and negative 4. We got to make sure we get them on there in order. This is a number line, so make sure you're on there in order. Now, you remember what we did before? We did some of these earlier this year. What did we do?
Test points.
Test a point, yeah. And you can test a point in every section if you want, or when your factors are just linear factors, your shading's going to alternate, so you don't need to check them all unless you want to. What number do you want to try? 0. Zero's in here. If I put a 0 in, I get a negative times a positive times a positive. That's called a sign chart. I just put the signs down. I don't really need the numbers. I can tell from the signs. So I put in a 0, and I put a negative factor, a positive factor, and a positive factor. What happens when I multiply those together? Is that bigger than 0? No. So that means this section is not going to work. Because these are linear factors, that automatically means these will work. As soon as we put a squared or something in there, then we are going to have to try every section. But as long as we don't have anything weird happening, we can go this way. And our answer is negative 4 to negative 1 or 3 to infinity. Now, let's try example 4 because it does have a squared factor. That does not change the way you start the problem. You're going to have zeros or dots on the number line at negative 2 and 5. This time they'll be colored in. Try every section. So I don't care what order you do it, it doesn't make any difference, but we gotta try them all. So I'm just gonna start with negative 3. If I put negative 3 in, watch it, this is going to be positive, isn't it?
Yeah.
This one's going to be negative. When I multiply those together, I put in negative 3. When I multiply those together, my result is exactly what I want, right? Negative, less than 0. How about when I put in 0? 0 gives me positive times negative Well, that's also negative. 6 gives me positive and positive. That doesn't work. So my answer is everything from negative infinity to 5. Since those are hooked together, don't split them up. Don't split them up. This is the whole shebang. Okay. Now, this is so cool. If a table, or given a table of values with equal width inputs, we can determine the degree of a polynomial by examining successive differences in the output values. Okay, so what that means is, let's look at that first table of values. This is kind of cool, folks. Let's find the differences. Okay, so what's the difference here? -1, subtract, right? What's the difference here? 2, right? We're subtracting, so -3 minus -2, -1 minus -3. What's here? 5, and here is 8. Okay, do it again. What's the difference here? 2 minus -1 is 3. 5 minus 2 is 3. 8 minus 5 is, now notice that the differences are the same in the second subtraction. This was the first subtraction. This was the second subtraction, the second difference. That means this guy is quadratic. When the number of the subtraction, or the number of the difference that finally matches, is the degree of the polynomial. So here was the first one, they didn't match, so it's not linear. Here is the second one, it did match, so it is quadratic. All right, quickly do the last one. It'll take me too long to get it written down. Degree of table B. Were you able to figure that out? 3. It's a cubic. Why? Well, here was the first differences. Are these numbers you got? Okay, they don't match, so it's not linear. It's not first degree. Here were the second differences. They don't match either, so it's not second degree. But my third differences did match, and that means we are cubic. Isn't that one of the coolest things ever? All right, last topic in this section, even and odd functions. We're going to have to finish this tomorrow, but let's at least talk about what even and odd mean. So the first picture there, the W-looking thing, is even. The second one is odd. I want you to look at their symmetries. When he says that an even function is symmetric over the x-axis, or over the y-axis, does that picture make sense to you? Symmetric over the y-axis means we can fold it this way and it matches up. To be even means if you plug in a positive number, you're going to get exactly the same thing as when you plug in a negative number. Think about the function x squared plus 5. If I plug in 2, I get 9. What if I plug in negative 2? I also get 9, which means on the graph, the point 2, 9 and negative 2, 9 are both on the graph. See how it's symmetric? That's what it means to be even. This is the definition of an even function. Graphically, they're symmetric across the y-axis. Now, an odd function has this behavior. Oops. If you plug in a negative, you get out the opposite. So think of the function y equals x cubed. If you plug in 2, you get 8. What happens when you put in -2? You get -8. So a negative input gives you a negative output. All right, that's symmetric about the origin, but we'll continue talking about that tomorrow. Have a good day. Didn't finish, so no homework assigned at this point, but it will be next time.